Judy and Patty and everybody involved with NIU Outreach for inviting me here. I've known Patty for quite a while and I'm very excited to finally get to come and see STEM Fest and see what she's done with the cafes. So I'm super excited about this. So tonight I am going to give you a talk of ice and fire, the physics of Game of Thrones. So how many of you guys here have seen Game of Thrones? All right, how many were dragged along by a Game of Thrones fan? Okay, a couple of you. Yeah, it's totally fine. I will tell you at the end of this talk, I have a physics problem for those of you that might be more on the romantic and less on the dragon fire entertainment scale. So there's some at the end, I promise. So the world of Westeros and the world of Game of Thrones has two basic forces fighting each other: fire and ice. And at the end, the second ice one I'll do will be for the romantics. And so I'm going to talk tonight about both. You've seen dragons and you've seen the wall, and I'm going to talk about how physics works in all of those. So the world of Westeros, you have all of the kingdoms. This is just Westeros. You can see Essos over there. All of the kingdoms, they're at war, and as you know, when you play the Game of Thrones, you win or you die, as Ned Stark unfortunately found out. There may be spoilers in here, possibly some curse words, but no nudity, okay? Sorry, I have to draw the line somewhere. And in this world of Westeros, you have a whole lot of magic, and that really doesn't come in until a couple of the later seasons, but you've got, in particular, dragons and fire. And in a lot of cases, magic sometimes has a pretty straight up physics, science explanation. So I'm going to do, before any of this, a quick little magic trick that you guys might have seen other magicians do. Just to show you that sometimes even things that look super magical have physics explanations. All right, let's see if I can do this. There's probably about a 50% chance I'll light my hand on fire. Dollar bill. So this is a cup of water, just normal water. This is a cup of alcohol, the kind you can't drink. Do. It's one of their favorite intro tricks, but all it was the water protected the dollar bill from burning, and the alcohol burned off really quickly. So the two together made a magic trick, an actual physics experiment, which is awesome. My hand does hurt a little bit, but we're totally fine. We can keep going. So, as you learned in season 1, hold on.
Winter is coming.
Winter is coming. But really? Well, maybe. I don't know. How do these seasons work again? So one of the hallmarks of the Game of Thrones world, of this entire mystical world, is the idea that seasons come and go without any regularity. And you've had this 10-year summer, and winter's coming, and the Citadel finally sent out the white bird, but no one's really sure how long it'll last, and this causes a lot of strife. But is it possible to have a planet like that where the seasons would be totally wonky, where you might not be able to chart when you have summer and when you have winter, and it might just be handed down through the generations that sort of this happens? So to start thinking about that, the first thing to think about is what causes the seasons on Earth. So here's just a quick poll. How many people think the Earth is closer to the sun in the summer? How many think it's closer to the sun in the winter? How many think it's about the same distance no matter what? Okay, so I will tell you that they did a poll of graduating seniors at Harvard, and when asked why the Earth has seasons, like some stupid percentage of them said it was because the Earth was closer to the sun in summer. So you beat Harvard. Nice job. So the reason we have seasons is not because we get closer or further to the sun, it's because we have a tilted axis. So, for whatever reason, this is very small on my computer. So throughout a year, the Earth is rotating around the sun, but you can see it's tilted just a little bit. And if you look over on the left, those are the sunlight. So the difference between winter and summer is that in the winter, the rays are they're coming in at a huge angle. You're not in direct sunlight. And then during summer, you have the direct sunlight. And this is why northern hemisphere and southern hemisphere go back and forth. But we have very regular seasons. And we have regular seasons because if you watch where our axis is, it doesn't move a whole heck of a lot. It kind of just hangs around. And we're pretty lucky that we have the moon, because the moon helps stabilize our axis. If we were to explode the moon, we'd go all wonky-like. So what would happen? So you've got two things here to kind of look to make Earth look like Earth. The first is we're going around the sun, and we're a little bit of an ellipse, but not too much. And we've got this nice, wonderful, stable axis. So what would happen if I started screwing with that stuff? Well, if we had something, these are not the exciting videos. Hold on. There's little planet. If I had a little planet orbiting a sun in something like this, it really would matter if it was closer or farther away. The seasons would all of a sudden be affected by that, because this is a huge difference. So when you're far away, the climate's going to be cold. When you're close, it's going to be warm. But this doesn't matter in Earth's orbit. But if you really started messing with it and created a huge elliptical orbit, that could happen. So that really might be what's going on in Game of Thrones. Maybe that's what's happening on the planet, that has Westeros. Maybe. But we also have this thing where the seasons aren't regular. So the seasons would be pretty regular here. So it's probably not this, but this could, do something. So what happens if instead we have a wobbly axis? So normally, the Earth actually has a kind of wobbly axis. Every 26,000 years, our axis moves around a little bit, sort of like a top, but you'll never notice. 26,000 years, and it's a very small difference. Well, what happens if it's not like that? Well, it turns out you end up with an extremely complicated way of looking at seasons. And what's really neat is that the Kepler mission just found a planet like this. They found something that could house Westeros. In 11 years, it goes through 30 degrees. So what takes us 26,000 years, they do in 11. So Lord only knows what season it's going to be at any point. You just don't know whether to wear Bermuda shorts or, a cloak, as you would. The problem is this is also really close to two stars, and water couldn't be liquid, so maybe not the right, but you get the idea. What's probably happening, though, is that it's a combo of both of these. And what this is called, and this is, I swear, the only graph I will have up here, I promise. And all it is, don't worry, you don't have to pay a ton of attention. All it is saying, if I look at how it orbits, if I look at how the planet goes around this really big elliptical orbit, plus how the axis is going all wonky, I get the thing at the bottom that tells me about how the seasons are going to go. So if you had a Game of Thrones planet that had some weird as heck elliptical orbit, plus this wonky axis, you could really have something where you aren't sure what season it's going to be. And if you remember way back to season 1, right before Arya tries to kill Prince Joffrey, which I wish she'd succeeded. We all wish she'd succeeded. They are having this conversation about the history of Westeros and how their planet used to have 2 moons. And one of the moons flew too close to the sun and exploded into 1,000 dragons. And if our moon would go away, it would send us into a wonky, wobbly axis. So, we have in the mythology of Game of Thrones the fact that they did have a cataclysmic event like that. That might have been why we ended up with the wonky axis and the Lord only knows what length seasons. So it's not too out of the realm, though George R.R. Martin came out and said, would you please stop trying to explain it, it's magic, all right? So whatever. Any science that came out of this, we did, not him, it was an accident. So, the moon that possibly created these wonky seasons also created, and this is, I just really like this quote, or this little scene, talking about what it's like to live on a planet where you don't know when winter's coming, and you don't know how long it's gonna last. And this is a neat scene between Bran and Old Nan. And I'm gonna fast forward just a little bit.
You hated stories. I could tell you about Sir Duncan the Tall. Those were always your favourites.
Those weren't my favourites. My favourites were the scary ones.
Oh, my sweet summer child, what do you know about fear? Fear is for the winter, when the snows fall 100 feet deep. Fear is for the long night, when the sun hides for years, and children are born and live and die, all in darkness. That is the time for fear, my little lord, when the white walkers move through the woods. Thousands of years ago, there came a night that lasted a generation. Kings froze to death in their castles, same as the shepherds in their huts. And women smothered their babies rather than see them starve, and wept and felt the tears freeze on their cheeks. So is this the sort of story that you like?
So let's hope our moon doesn't explode, because this could be our future. And let's hope it's not made of dragons. So once the dragons came into the world, they came in to Westeros with Aegon the Conqueror and his two sisters, Rhaenys and Visenya. And as the story goes, they flew from Essos on their 3 dragons, Balerion the Black Dread, who breathed black fire, and one of the first things they did was attack Harrenhal, which is this great fortress that was built to be absolutely impenetrable. Like unbelievable amounts of gold went in to build a fortress that no army could conquer. And they were right, no army could conquer Harrenhal from the ground. So these dragons come in, and it is said that the dragon's fire was so hot, it melted the towers of Harrenhal, which is pretty darn impressive to melt. And I'm gonna assume it's granite, they weren't specific on the construction materials, which you'd think in like, what, 3,000 pages he could have told me that? But you know, maybe it's coming up in the 6th book, eventually. So the dragons come in and melt the towers of Harrenhal. And I will say that this is still from the show, but there's a lot of other art, and it looks almost like dripping melted candles. So my first question is, well, could a dragon do that? Like, let's say I did have a dragon that was breathing black fire, which is kind of ridiculous, but I'll talk about it. Could it actually melt stone? Well, what does it mean to melt stone? So when you melt something, you're taking it from a solid to a liquid. And we've all, well, I mean, anyone that's gone to Hawaii, plus anyone that's watched that awesome YouTube video of the lava taking the, over the Coke can, all of those, we've seen melted stone. That's what lava is. It's flowing stone. And so in the case of granite, what it is all of the molecules that are sitting happily together. You've got feldspar, you've got silica, you've got lots of different things together sitting, and they can get hot enough to slide over each other and become a liquid. So that happens, lava happens at about 1300 to 2400 degrees Fahrenheit. And you can melt granite at about 2800 degrees Fahrenheit. So, this is pretty hot. Is it possible that dragons can breathe fire that hot? Because that's the obvious question. And considering, again, that Martin did not mention in his books the temperature of dragon fire, I had to do a little sleuthing. So, different types of fire are different temperatures. And the closer you are to white, the hotter it is. So black fire, kind of ridiculous, but white fire, not so much. And what's interesting is in all the fan art I've found, because apparently I spend hours on the internet finding fan art for Game of Thrones, Valerian the Black Death actually breathed white fire. He was a black dragon, and we're just going to assume that it looks black next to a black dragon or something. But bright white fire ends up being about 2,700 degrees Fahrenheit, so it really could have melted granite. So this dragon flying in to this castle that could only be attacked from the air and turning it into a melted candle wax mess. If this dragon was as hot as the legends say, he really could have done that. It's a neat way to look at dragon fire, I think. So now, you know, in the story, after years, sorry, I have another demo for you. I forgot the order I was going to do the demos. I like doing fire demos. So the idea of letting stones melt, that's not something you're used to. Stones aren't supposed to melt. Turns out there's a lot of things that you can light on fire that you'd be really surprised about. Sorry, my second career was going to be in combustion engineering. So this is both a trick for how to store cleaning products, and if you go camping and and it's raining and don't want to bring matches. This is just straight up steel wool. This is steel. Steel is not supposed to light on fire. This is a 9-volt battery. Do not store this in the drawer with your steel wool. And it's actually rusting and combusting at the same time. And I'm not going to get that near the rubbing alcohol. And that's the water, right? Yep. Okay, feel a little better. So it turns out that in a lot of cases you can't. There are things that are flammable that you would be, you know, surprised at, and steel wool is one of those. And I will tell you that it's a really great camping trick because it'll happen even in the rain. So use that. So back to dragon fire, which is a little more reasonable. So the question I had, Valerian's supposed to be this huge dragon, the biggest of all the dragons. Well, is that why his fire's so hot? Is it because of his size? When dragons grow up, what happens, you know, does it change the color of their fire? We've got 3 dragons, and I gotta say, they look kind of badass. Why isn't Danny just going on in? So I will show you a bit of why.
Is it done then? Do they belong to me? Hindas necessitida. This is done. You hold the whip. Zadrizes gustaris daur. Nigei daineres tion masmo en tagerio letra. En Valeria veco anagarexan. Valeria munioengos nuihis isa. Dogageris. Axios entas, mentios entas. Kilomic pilos lyö valectorios.
So there, even if she got Tyrion on that dragon, there's no way she'd be melting the Red Keep with that. So she really has to wait for her dragons to grow up, not just to grow in size to carry her, but to actually grow in heat to be able to harm the castle the way she wants to. And so I have another little fire demo. This is my last fire demo. I'm sorry. And this is my version of indoor dragon fire. It's not hot. It's not white hot. It's orange. It's baby dragon hot. It's also, if you have a child's birthday party and want to really impress them with the candles on the cake, this is the way to go. Oh, this is just a little bit of cornstarch. So nothing fancy. You'll see magicians' shops sell this called Lycopodium Power cornstarch. It's 99 cents a box instead of $6 a bottle. Get this stuff instead. I can do that better. I'll try it one more time and then I'll be done. And I might be able to play with it later. Okay, so this worked great before. And I apologize for just covering your stage in cornstarch for no apparently good reason. But you can see the demo online and it shoots fire pretty well. So I'm sorry, that's my indoor fire demo. But in case you haven't figured it out now, House Thompson is declared for House Targaryen. You know, after Oberyn, I was kind of thinking of Martell, but definitely going Targaryen. So, one of the other neat things that dragon fire can do is create dragonglass. And there's a whole lot of people at the wall that are super excited about this stuff. So the question is, what is dragonglass exactly? Why is it special? And what does that have to do with White Walkers? Well, obviously there's some magic in here. But what a glass is a very, very interesting thing. So glass isn't the same as like a salt crystal or even like your lead crystal bowls. It's very different. What it is essentially a very slow moving liquid. So unlike a salt crystal or sugar crystal where all the stuff is sitting where it should be, glass, it was kind of like someone was playing freeze tag with the molecules, where they're all kind of wherever they are and someone said stop right there, and they did. So they're not moving, so they're not really a liquid, but it's still kind of weird. And that's what happens with dragonglass, which is also obsidian. In the books, they go back and forth between the two. In the TV show, I think they just keep it at dragonglass. But what it is silica with some various other minerals in there. It gets really, really hot. It's usually created from lava and cooled extremely quickly. So when you have lava cooling, there's two things you're going to get. You're either going to get something like this, which is the lava rock you pick up on the beach in Hawaii, maybe, or you're going to get obsidian. And when it cools very slowly, you get rocks. When it cools very quickly, you get glass. And one of the neat, neat for the science of glass reasons, not for various other geopolitical reasons, but at the Trinity bomb testing site, they created something called trinitite. Accidentally, that's not been seen anywhere else. And when they were testing bombs and dropping it, the sand from the ground was picked up, melted, and cooled in the air, and fell to the ground as green trinitite. And people still, I know my boss used to have a piece of it on his desk. You can't really get it anymore for obvious reasons. But it was a really neat thing that no one expected. It was a side effect no one expected. And in the case of dragonglass, what it is really just the same thing as obsidian. But in this case, it's fire and ice together. It's a weapon made by fire, forged in ice, and apparently it has some fantastic properties. Thanks, as Sam was very excited to see.
gonna work.
So, as Sam the Slayer found out, dragonglass has some pretty awesome properties. So, what is the difference between steel and obsidian at really cold temperatures? I mean, really, is that something that could happen if you ran up against a White Walker? So, steel is very, very strong, but in very specific circumstances. Every day, holding up buildings sounds great because we don't really have that extreme temperatures. But as soon as you start getting pretty cold, steel gets very brittle, and right around negative 40 degrees Celsius, you can just crack it. So the idea of the White Walker reaching up and grabbing the steel blade and shattering it isn't too bad, assuming he's below 40 degrees Celsius, which I think we can safely agree he is. But obsidian is extremely strong all the way down. And so it can get very cold and still stay very, very strong. So obsidian, if I would much rather have an obsidian weapon at negative 40 degrees Celsius than steel. And so the pictures over there on the left, what you have all the way on my left, your right, the all pitted, funny looking one, that's the edge of a steel scalpel under an electron microscope. The one on the left is the same size, same magnification, and it's obsidian. And what you can see is, heck, even if the obsidian cracked, it's still stupidly sharp. So if that's in the White Walker, and the White Walker was cold enough to crack obsidian, who cares? He's still getting it. And there's a lot of scalpels that are made of obsidian because it's much, much, much sharper. You can sharpen it to an amazing degree. So obsidian's a pretty neat thing, and it even in it's not like super weapon, but even in not Westeros, it's a pretty neat thing to use. So talking about White Walkers brings me to, of course, Jon Snow. I think he's alive. Just saying. I was talking to a friend about this. My theory with Game of Thrones is that unless you see a head on a spike, they could still be alive. And the head has to be detached completely from the body. And then you know they're done. Jon Snow, couple of stab wounds, who knows? Pretty fun climb. And that looks like a pretty awesome defense system. So the wall is, in theory, a fantastic idea, right? It's hard to climb, clearly. You throw arrows at it, anything, you're not gonna, a battering ram isn't gonna do a whole heck of a lot. It can't catch fire, so dragons aren't gonna be that effective against it, which is like the one thing in this world the dragons aren't gonna be effective against. Oh, the projector's a little off. enemies have to attack tunnels or castles. So you can, you know, as you saw in the Battle of the Wall, which was amazing, you ended up having 300 men defend against a 100,000 person army. The wall is that good. Okay, so awesome, they built it. Is that possible? Was my next question. So ice has some interesting properties. So if you think about what kind of forces is the bottom of the wall going to be feeling at some point? So ice has a density of about 917 kilograms per meter squared. That means for 1 meter squared, you have a kilogram of ice. Okay, that's a lot of ice, meter squared, big wall. Then you have pressure. The pressure something feels is how much force it's getting per area. Okay, so let's assume we have 1 meter at the bottom of the wall. What's that gonna feel? About 100 elephants per square meter at one little square at the bottom of the wall. That's gonna be hard to support. So if you have this 700-foot wall, that little part at the parts at the bottom, are they even gonna be able to support it? Is ice gonna crack at that? And then the even worse question, turns out ice is really hard to deal with. Because unlike everything else, when there's pressure on ice, when something pushes on it with enough force, it decides to melt. So at the bottom of the wall, you've got 100 elephants per square meter, and it really likes to melt when heavy stuff's on it. So the bottom of the wall isn't gonna last as a solid for super long. And why ice melts is an interesting question, when it's pushed on is an interesting question. So ice, and you can see this by looking at every glass of water. When ice gets cold, when ice freezes, it actually expands and takes up more space, so it floats. Well, if you try and push it real hard, it can't stay in that nice structure that makes it a solid. You're pushing the atoms, the molecules back together, they move all over each other, and they go back to water. So unlike everything else, you push on it really hard, it wants to be water again, and it does. So that the whole reason it becomes water under pressure is because when it gets cold, it expands. There's a few other substances that do that. Plutonium, I mean, that was interesting to learn. Who knew? Gallium, a few others do it, but it's a really different thing. So what would happen to the wall with these two things? You've got all of this weight, and under this weight, it's gonna melt. Well, it turns out it's gonna do it quite a lot. So all of these equations, both the cracking and the melting and all of this is very, very complicated. And there's a whole section of geophysics that studies this for glaciers, because it turns out we have giant ice rocks. And so glaciers study this, and for something this size, I can't go through the math because this was all done computationally. You end up with something like this. If you want your 700-foot ice wall of Westeros, you're gonna end up having to have it about 6,000 feet across. So you've got this nice ice pyramid of Westeros. Is that really gonna do anything?
Do you have a chicken sandwich?
So that is, for those of you that are cyclists or runners and run up hills, this ends up being about a 25% grade. One of the famous triathlons in Maryland is called Savage Man, and it has the Wall of Westernport, which is the same grade as the actual Wall of Westeros. And though it is very hard to get up the Wall of Westernport, you get a brick in a road if you do it. I have not done it. People fall, and if you ever want to watch people falling on bikes, this is pretty fun. So they YouTube it, they do a highlight reel every year. One of my friends was on the highlight reel this year. But basically, if they had decided to build the Great Wall of Westeros, they would have built an incredible sledding hill for the wildlings. So this is not going down as the most effective defense mechanism. So I promised that at the end of the talk, I would do a problem for all the romantics that got dragged along, okay? And I'm gonna just assume that everyone here has seen the Titanic. And one of the great problems of my youth was something that I am sure you all thought: there was room on the raft. Okay? Jack is dead. He doesn't need to be dead.
She let go.
Rose is alive. She let go. They could have played cards on the raft, and women everywhere wouldn't have had to reapply mascara, and the world would have been a better place because there was room on the raft. So I've wondered this literally since I was 18. And then, after this meme came out, James Cameron came out and said, oh, it was because of buoyancy. I was like, oh wait, I can do this one. So as soon as Cameron said buoyancy, I'm like, I got this. So I decided I was gonna do this problem and see if Jack really was gonna live or die. Should I blame physics or Cameron? Just wait for it. So we start with a sinking ship and an entire very cold ocean filled with debris. And one piece of debris is a door. I'm just gonna assume it's a door. It looked like a door, no one was specific. So anytime you have something floating in water, water's pushing it up with a buoyancy force. And this buoyancy force is equal to the density of water, gravity, and the volume of the water that's being pushed out of the way for the door. So I'm gonna assume the door's floating just at the surface, most of the door's under there. Doing that, I get that the buoyancy force is gonna be about 2,000, and it needs to be this exact. 2,490 newtons. That's with a door. Let's add some people. Well, first, the door is pushing down, it's being pulled down with gravity. And with that, I looked at the density of oak, because there are three woods that were used in the Titanic: oak, pine, and teak. Oak has kind of the middle density. It was probably an oak door, so I went with oak. So, doing all of that, just the door floating is gonna be 1,920 newtons. So we ain't got a lot of room for people right now. So let's add Kate. And interestingly, I don't know if people remember this, when it came out, there was a big hullabaloo because she was larger than most actresses in leading lady roles, which made me want to punch people in the face. So because of this, it was not difficult to find her weight, which is terrifying. So it turns out that Rose weighed 125 pounds. It was like literally in every women's magazine in 1998. Seven or whatever. So she's pushing down with 549 newtons. Let's add Jack. He was a skinny little thing. Also, a lot of controversy around how skinny he was. It was not hard to find his weight either. 161, very exact. I mean, 161 pounds, so that is 712 newtons, and you can see where this is going. Not well. So at this point, we're a little overburdened. The door was never gonna hold them both. Interestingly, let's assume that Rose got on the damn lifeboat like she should have instead of trying to kill Jack for 19 minutes. And let's assume Jack finds the door on his own. He ain't gonna make it either. That extra 2 pounds, he shouldn't have had a burger for lunch. He wouldn't make it. But if we have the door and Rose, we're cool. So, unfortunately, you can't blame, well, what's interesting, as you can see, is we have 2,470 newtons. She just barely makes it. Just barely. So I said that I assumed oak, because I figured oak, whatever. If it was teak's so much denser, they're all dead. If it was pine, they both would have lived. So you can also thank oak, well-made doors, and buoyancy for the fact that they're dead, but it wasn't Cameron. So I'm sorry, but I hope this answered what, if you're like me, a long-standing question from your childhood. So I hope you guys had a lot of fun and learned some Game of Thrones, and I have a lot of time to answer questions, and I'm happy to answer questions and walk around and talk with you all. So thank you so much.